Yes.
Yeah, okay. Yeah, thank you. I'm sorry for the inconvenience. Yeah. So I will be talking on the role of scatterometer data assimilation in the simulation of boundary layer flow of tropical cyclones. I'm working in National Atmospheric Research Laboratory, and my research collaborators are Arpita Munshi, Govindan Kutti, and Sanjeev Dev. So this is the outline of my talk. So I will give brief introduction to data model experiment, what is boundary layer dynamics, and then the conclusion. Before starting this study, we have done some rigorous analysis of how the tropical cyclone intensity is represented in various reanalysis data sets. So we have taken 28 tropical cyclones over North Indian Ocean during the period 2006 to 2015. And we have seen that there is, this is the contingency table seen on the left in the slide. So we have seen on the y-axis, you can see the IMD observed intensity of the cyclone, and y or the horizontal axis shows the ERA analysis. So we have taken ERA interim, GFS analysis, Japan reanalysis, MERA2, CFS reanalysis, and ERA5. And what we have observed that GFS, CFS are able to capture the most intense stages of tropical cyclones, followed by the ERA5 data set. And the structure and intensity are better represented in GFS analysis, followed by ERA5. You can see here ERA5, it has represented cyclonic storm and severe cyclonic storm better than the other reanalysis. Even in CFSR, it is better represented. And GFS analysis captures the evolution of tropical cyclones more realistically, followed by ERA5 reanalysis. So having this background, we have decided to generate a mesoscale reanalysis for studying the tropical cyclones over the North Indian Ocean. So we have taken 5 cyclones over Arabian Sea and Bay of Bengal basin. Oki was formed over Arabian Sea during 2017. Mekunu, Luban, and Titli, they are formed over Arabian Sea and Bay of Bengal during 2018. And Fani was category 5 cyclone, which was generated over Bay of Bengal during 2019. And the satellite-derived wind data, ocean surface wind data, is very important during the cyclone time, as there are very less observations available over the oceanic region. So we have taken 3 scatterometer or ocean surface wind retrieved from OSCAT2, ASCAT, and WindSat. So OSCAT2 is our SCATSat-1 satellite, ASCAT is our Coriolis, and the WindSat sensor is our METOP2. And the error in the wind speed and direction for OSCAT2 is 2 meters per second, and error in direction is 18 degree, and which is lesser compared to ASCAT and WindSat observation. These are the details which I have given for the assimilated data. So coming to the model configuration, so we have taken the bigger domain, we have used WRF model, and we have considered South Asian domain spanning from 30 degree east to 140 degree east. And we have considered 2 domains. One is covering over the Arabian Sea, and another over the, another over the Bay of Bengal region. And we have generated background error using the independent data set of 2017, and we have calculated the background error covariance matrix over this domain using the NMC method. And so it is calculated using the difference between the pair of forecasts having different lead times, but each having the valid at the same time. And we have taken the resolution, horizontal resolution, as 18 kilometer over the South Asian domain and 6 kilometer over the nested domain. And we have taken 64 pressure levels and used Mercator projection. We have integrated with 60-second time step, And the model physics options we have used is for a unified NOAA land surface for a land surface model, MYZ scheme for PBL physics, then RRTM Dudia scheme for long wave and short wave radiation, Thomson scheme for microphysics, and Kenfish scheme for cumulus physics. And this is the flow chart is showing the methodology used for scatterometer data processing. And we have taken level 2B data and we have sorted in the each 6 hourly files. And we have done the quality control and integrated all the 3 data sets in one file with the data processing. And we have used hybrid data assimilation, that is ETK 3DVar method for for improve the initial conditions at each 6 hourly interval. So this is the cost function, and the highlight of the ETK 3DVar method is it gives weightage to the static background as well as the ensemble generated background error. So here we have given more weightage to the ensemble generated background error, that is 75% compared to the static background error. And this is the cost function showing. So errors, so at each 6 hour, we are taking the boundary conditions from GFS, and each model forecast is at 6 hour. We disclose the spin-up time, and for the next 7th hour, we assimilate the scatterometer data. But we have done the 2 experiment. In one experiment, we have taken in-situ observation, atmospheric motion vector, and radiance data. And in a second experiment, we have just added the scatterometer winds to understand how whether it will improve the overall dynamics or representation of dynamics in the reanalysis mode. For ensemble method, we have considered 80 ensembles, and we have calculated the difference first between hybrid experiment, that is control plus scatterometer minus the control. And we have used the IMD best track data for the validation of track and intensity. And this is the snapshot just showing the how a number of observation at each 6 hourly we have assimilated. So normally the SCAT set data is available over North Indian Ocean during 0 and 6 UTC, while the SCATSAT is available at 0 and 12, while the WindSat is available around 12 UTC. So after integrating all these data sets, we get better coverage over the North Indian Ocean, around 30,000 observations. So these are the, now I will show you some of the results of the simulated cyclones. So the left panel shows the extremely severe cyclonic storm Fani, the observed and simulated track. So there are some diversions in the track in the initial stage and the dissipation stage of the cyclone for the Fani and as well as the Oki. The same is reflected in the position and intensity error. So we can see at some part of the during the intensification process, after assimilating the scatterometer, the intensity error reduces, and at some point the track error also reduces using the scatterometer data. So this was for tropical cyclone Fani, and this was for the tropical cyclone Oki. Now what we have done is we have calculated to understand the boundary layer dynamics. We have considered some parameters like convergence, then vorticity and wind shear to understand primary and secondary circulation differences in the reanalysis, the generated reanalysis. So this is the difference in 850 HPA convergence using scatterometer and without scatterometer reanalysis data. So we can see that there is an increase in convergence on upwind quadrants and increase in the divergence in the downwind quadrants, which shows that there is a strengthening of primary circulation. This is for the tropical cyclone Oki. I have taken not each 6 hourly, but where I am seeing the prominent differences, those times only I am showing the differences. And this is the for tropical cyclone Oki, which was generated over equatorial Indian Ocean and traveled over the Arabian Sea. So here also we can see there is a increase in the convergence of upwind quadrant and decreasing in the increase in the divergence in the downwind. So there is a change in the primary circulation using the reanalysis with scatterometer data. Now we have seen the primary circulation. The secondary circulation of the cyclone we can see through the relative vorticity at 850 hectopascal. So we have seen in the first panel there is an increasing relative vorticity over the eyewall region and decrease in the eye region of the cyclone. So there is a strengthening of circulation in the vorticity field over the eyewall region and the reduction in vorticity in the eye region, which shows that there is a strengthening of secondary circulation over the near the eye of the cyclone. Similar differences we calculated for the tropical cyclone Oki, but however this difference is seen near the eye of the cyclone here also and not over the other cyclonic region. Now, the large-scale instability is also very important in the cyclone formation and its intensification. So we have seen the boundary layer shear, which helps in enhancement of the large-scale instability. So in the this is for tropical cyclone Oki. So we can see there is an increase in wind shear in upwind left quadrant, which shows the enhancement of wind shear and increase in the large-scale instability, which supports the rapid intensification of the cyclone in the reanalysis dataset. So a similar thing we calculated for the tropical cyclone Oki, but we have seen during the intensification stage, which was near the southern tip of the India, we can see there is an increase in the intensification of the wind shear in the left corner, not in the left corner, but is the eyewall region, which improves the large-scale instability of the cyclone. And spinup, after seeing the instability, we are seeing whether the rapid intensification is reflected in the reanalysis. So we calculate the azimuthally average maximum wind speed around the tropical cyclone center, and we have plotted for each day whether the average maximum speed shows the improvement. For that spinup parameter, almost control and hybrid parameter shows the similar trend, and we see the sharp increase in the spinup when the tropical cyclone underwent the rapid intensification. So the large-scale deep pressure enhancement help in developing the strong cyclonic rotation and helps in developing the large-scale instability. So coming to the conclusion, the mesoscale reanalysis of high resolution is generated using ETKF 3DVar technique to study the tropical cyclone dynamics. And the simulated track matches well with the IMD best track data. The large errors in position and intensity are seen in genesis and dissipation stages of the cyclone. The reanalysis using scatterometer wind data shows better representation of intensification in a tropical cyclone Oki and Fani, increase in convergence on upwind quadrants and increase in divergence in downwind quadrants indicate the strengthening of primary circulation of the reanalysis. Increase in vorticity in the eyewall region indicates the strengthening of secondary circulation of the cyclone. Increase in wind shear in upwind left quadrant and indicating the enhancement of large-scale instability. Thus, deep pressure enhancement help in developing strong cyclonic rotation by arresting the suppression of downdraft created by precipitation. It indicates the development of large-scale instability. Thus, the representation of tropical layer boundary layer processes in high-resolution mesoscale analysis is improved by data assimilation. So, we are further analyzing the remaining cyclones. And I thank you, ISDA, for giving me the opportunity to present in the online sessions. Thank you.